To the super lecture session 7, and my name is Santiago Badia of University, and I will chair the first speaker's lecture, and Professor Wolfgang Wall will chair the second subject. Okay, so first I would like to introduce the first lecture. Professor Santiago Badia, and he received his PhD from UBC in 2006, and he is currently a professor at UBC. And his research interests include grid flow and related coupled advanced physics problems with emphasis on restructuring interaction and magnetic hydrodynamics and massive power domain composition. And the title of his talk is Implicit multiphysics solvers. So Professor Badia.
Thank you very much. Yes, I'm going to talk about scalable implicit solvers for multiphysics. So, people here is the people that work with me in the state of fields 20 kilometers to the south from where we are now. So, I will split the presentation into two different parts. In the first part, I will talk about scalable solvers. In particular, our last efforts towards the development of highly scalable domain composition methods for finite element computations. We are going to work with balancing domain decomposition by constraints preconditioning and apply it for a simple quantum-physics problem. And finally, I will also present another implementation of these methods that allows us to have very nice with scalability up to the order of 100,000 cores in Blue Q in Zurich. After I will present these scalable solvers and how we scale, I will try to go to multiphysics. And the way we go to multiphysics, our approach is the following, the one that we have here, in which what we consider is a recursive block preconditioning strategy in such a way that we start with a complex multiphysics problem and we split it into pieces in order to end up with one physics solver. Then, for these one physics solvers, we're going to use the methods that I've collected before and go to large scale simulations. In the road towards multiphysics solvers, I will also present some experiences for the compressible course. So let me start with the first part about highly scalable solvers, and I decided to introduce a little bit the WCCM conditioner that we are using, since probably most of you don't know. So let's assume that we have some domain and finite element partition of this domain. For this talk, I will assume that we are using H1 conforming finite elements, continuous alerting, even though all these things can also be applied to this continuous alerting in a quite straightforward manner. So, for the first part of the presentation, I will assume that we have a problem with the linear form which is symmetric and worse, for instance, of Laplacian solver or linear elasticity. And okay, we are our finite element approximations, and at the end of the day, what we have to do is to solve a linear system. Our matrix here can be large, and certainly sparse, and due to this, symmetric and positive. So, what we want to do is to solve this problem using the domain decomposition framework for efficiently used distributed memory machines. For instance, here, as just as an illustration, we have a very silly 2D mesh that we have split into 12 parts, and with this domain decomposition framework, you observe that we have we have classified our nodes between interior nodes, those white nodes, and the interface nodes among subdomains, which are the red nodes. Usually, we send every one of the subdomains to every one of the processors that we have, distributed memory machine. So, what BDC is? BDC, balancing domain decomposition by constraints, was initially proposed by Norman, and the idea is the following. Here we have our finite element space, which is, for the moment, let's say, in this presentation, we assume that it's continuous. So we have continuity among subdomains. And if we want to solve the problem, distributed memory machines, it's a quite hard task. It's not acceptable to think about writing the full complement on the interface and solve it within one processor. This is not something that you can efficiently do. So you have to do something else. And the idea proposed by Dorman was to replace the finite element space, which is continuous, by another one, which is discontinuous. So you introduce discontinuities going from here to here. You only choose just a small set of the red nodes to be the nodes in which you enforce continuity. But the rest of nodes now are global. Global for discontinuity among subnets. This is an illustration of the kind of space that we have in limits. These red nodes here are usually called core degrees of freedom. And in this illustration, we have chosen these core degrees of freedom to be the corners of our partition. So you have observed that we started from a continuous problem, and now we have defined a new finite element space with relaxed continuity. You can now imagine that, again, this is just a 2D illustration, but in 3 dimensions we start with lots of nodes on the interface in this space, and in this other space we have a much smaller set of nodes that couple subdomains. So you can start thinking about working with a Schur complement for this space. Certainly your solution is here, so somehow you have to inject the function that you have here into your space in which your solution belongs to. So this injection is very simple. You just take the mean values of these nodes in order to get the solution in this one. So it's very simple injection from the discontinuous function to work with. Once we have this injection, what we do in this preconditioner is to solve our original problem, for instance, of some solver, in the space with relaxed continuity. You get a solution which certainly is continuous among subdomains. You inject it into the space, into your space, into the continuous space, finite elements, and finally you inject it here, and finally you take the value of the interface of your solution and you extend it, you use a discrete harmonic extension in order to correct the value in the interior nodes. This extension is nothing but correcting the interior nodes in such a way that the residual in the interior is now 0. And it only involves global dividend problems, which are very parallel, so it's embarrassing the parallel test. So if you prefer, we can also write it in the algebraic form, in which now, instead of having our assembled matrix A, we have now distilled A, which means that we have only assembled the red nodes here. We have not assembled those, it's also assembled. We are only assembling the core degrees of freedom. So we solve this problem, again, we get it here, and now we're setting this discrete harmonic extension in order to correct the interior values. Have this expression here, where we have to invert a matrix which is globe diagonal, so embarrassing the problem. Okay, but the question now is how do you solve this problem, this BDDC problem, in an efficient way? So the main problem here is how do you compute this problem? How do you implement it in an efficient way? So the idea is that, okay, we take our BDDC space, this continuous function that we have here, and we split it into 2 parts, a fine part and a coarse part. The fine part is very simple. Are the functions that are 0 on the coarse degrees of freedom. That's to say, the functions that are 0 on the red nodes. Here, very simple. With regard to the coarse component, the coarse space, the complement of this one, in order to have the whole BDDC space, which is what we call the coarse space, and this, we enforce this space to be A orthogonal to the fine one. This is a very important property of BDDC. The coarse space, we define a coarse space that is A orthogonal to the fine space. You will see that's very important for implementation of space. So once we have this A orthogonality, we can compute the BDDC problem as 2 independent solvers, the fine grid and the coarse grid. We can compute them independently because they are A orthogonal. So how do you compute the fine grid? Okay, the fine grid is to solve the original problem, but in this fine space, so we are fixing the value on the red nodes, on the only nodes in which you enforce continuity among subdomains. So since you are imposing the values on the red nodes, the problems that you have to solve in order to compute the fine component are simply local problems. So this is something that you can efficiently do in parallel. It implies to compute local constrained Neumann problems. Neumann problems constrained only on the red nodes. So for the moment, so far so good. We go to the coarse problem, and the main thing here is to define a coarse space, a coarse basis function, a coarse basis space that is orthogonal to the fine one. So we have here the basis for the coarse space, and here these are just coarse shape functions, and we have one shape function per red node. For instance, for this node here, it's going to be a function that is 1 in this node, 0 in the rest of the red nodes, and in the white nodes, we want them to be orthogonal. So we have to solve this problem. And again, we have to solve a problem with 0, our problem with 0 right-hand side, and we are enforcing the values on the red nodes. So again, this problem can be computed in parallel. It only implies local constraint Neumann problem. So this is something that we can efficiently compute in parallel. For instance, for this node here, it only involves constraint Neumann problems in the subdomains shared by the node. So again, something that we can also compute in parallel. Here we have in a circle, into partition of a circle into 9 subdomains. So we have here this corner among these 3 subdomains, and here we have the shape function, the core shape function related to this corner degree of freedom, this core degree of freedom. As you can observe, the support of this shape function is only the 3 subdomains surrounding this course. So once we have this basis, which is orthogonal, the only thing that we have to do is to compute the Galerkin projection of the original matrix. We compute this matrix. This is like an element assembly, let's say, that we parallel. And you have your AC, your coarse matrix, that you can solve. You will see that we have different options, but the idea is that this coarse matrix now is very important for the performance of our methods, because for the performance of this preconditioner, because it allows you to have a constant number of iterations when you go to larger scale. But on the other hand, it introduces the potential loss of parallel efficiency, and we increase the number of processors. So it's good and it's bad. When you go to the analysis of these methods, it was done by Mandel and co-workers, and if you check which is the condition number of these methods of the preconditioned matrix, you can also we have the following values. Capital N is the size of the problem we want to solve, and B are the number of processors that we are going to use in our simulations. So we consider weak scalability. And weak scalability means that in the process of weak scalability, we increase the size of the global problem in the same proportion as we increase the number of processors that we are using. In such a way that the local problems in every one of the processors is fixed, remains constant in this weak scalability analysis. So this is, if you see here the condition number that we get from the theory, you observe that this method is weakly scalable because it only depends on n over p, which is the local problem size. Let's go to corners. For the moment in illustration, I was only considering as coarse degrees of freedom corners. So if we use as in the illustration only corners in 2 dimensions, the condition number is very good. It's something like this, only affected by the local problem size, like the logarithm. And this is very good because it's quickly scalable. It does not depend only on n or on p, only on n over p. But when we go to 3 dimensions with only corners, we get this additional factor, this additional n over p, that makes the method not so robust when you go to 3 dimensions, because n over p, the size of the local problems, can be very large, of the orders of 10 to the 4 or 10 to the 5. So when you go to 3 dimensions, it's much better to put something else in the course problem. And it is to include additional course degrees of freedom. So what people does in this case is to introduce an additional continuity among subdomains. And the type of continuity that you have to enforce is the mean value on edges of the partition or a mean value of faces. So as soon as you do that, you get rid of this coefficient that you don't want, and putting edges or faces in 3D is a big deal because you can improve quite a lot the number, you can reduce quite a lot the number of iterations. So here, for instance, we have a picture of the shape function related to the portion function related to an edge. So we have this edge communicating these two subdomains, and this is the shape function related to this edge. Here, this function, you can check that the mean value is continuous, but the function itself is discontinuous. So now, how we are going to implement these methods. First, let me say why we consider that BDC methods are let's say, quite interesting approach for students. The first thing is that it allows for mathematically support extremely aggressive coarsening between levels. So we can have a reduction of 10 to the 5 and 10 to the 6 between the size of the fine problem, of the original problem, and the one of the coarse problem. The coarse matrix, even though we have that, the coarse matrix is very similar to the original finite element matrix. It has a quite similar sparsity. So this is also a very good thing. Third, as I said before, to do this pure semantic property, the coarse problem and the fine components can be computed in parallel. This is something that's very important. And another very important thing is that all the local problems involved in this BDC method, like the Bondman, the Implicit problem, and also the coarse problem, can be highly short problems. Instead of solving these problems by the method, you can just put one cycle of A and G and you get with this solution. And finally, due to property 2, you can also consider a multi-level extension of these methods, as it has already been exploited by some authors like WCCM. So the first two things are something that you can easily get in your implementations, and now let's see how we exploit in our implementation of the method the third property here, computing parallel coarse and fine components. So the typical, the naive implementation of this kind of methods would be something like this, in which you have P processors and you have P subdomains. So you have some kind of a one-to-one mapping among subdomains and processors. So every one of these cores here has a piece of the mesh. So all the cores here have fine duties. They have to solve difficult problems, non problems, and at some point, just some of them are going to have coarse duties. I say just some of them, a very few ones, because the coarse problem is much smaller than the original one, so it doesn't have any sense to try to solve the coarse problem with the whole of them. So you can check that in this process there are lots of idle here. Most of the processors are waiting when those with coarse duties are computed. So this is a problem, and you can easily check that it has lots of implications in terms of numerical performance. And the other problem is memory, because the coarse problem increases with the number of processors, so you easily exceed memory in the cores that have coarse and fine duties. So our approach to the problem was to overlap the computation of the fine component and the coarse component of our solvers. This way we can, as I say, overlap these two computations, and in many situations the coarse part, which is the one that can harness scalability, can be masked by the fine one, which is embarrassed in the parallel, getting a perfect with scalability. For the coarse problem, we can consider both OpenMP or MPI type distribution of the solver. Okay, so in order to get this overlap implementation, what we did was to start looking at the VDC method, for instance, applied in a precondition conjugate way. So here we have so many tasks, for instance, the setup of the preconditioner, and at every iteration, the application of precondition, among some other things. So what we did was to take all the different tasks that we have in our implementation of the VDC method and map it in one of these two columns: fine-grid tasks and coarse-grid tasks. And what we observed was that there were 3 overlapping regions, and that all the coarse computations could be overlapped with fine units. So this was quite good news, and we implemented it. So as you can imagine, it requires some quite code factor, since we have now a multiple program, multiple technical implementation of the VDC. We did it in our code, MPART, which is a free software code. It's a finite element multiphysics parallel software. It was originally designed for multiphysics applications using block preconditioning techniques, and for the one physics problems, the VDC methods that I have introduced before. So we have interfaces with sparse direct solvers and also ANG preconditioners for the local problems. First, let me show you with scalability. In Helios, in Japan, we are solving a boson problem in a Q1 finite elements, a uniform partition. We are going to increase the number of cores, and we are going to use direct solvers for the local problems and also for the coarse problem. For the coarse problem, we have one node of the machine, which means 16 cores. And we are going to have 2 different local problem sizes. This is going to be with scalability, so we increase the number of cores in the same ratio as we increase the size of the global problem, and so we keep fixed the local problem size. And we have 2 figures, one for 27,000 nodes per core and 64,000 nodes per core. So here, this one here and this one here is what we get before this overlapping implementation of the algorithm. We start losing scalability from the very beginning. And with this approach, what we can observe, for instance, using 16 cores for the coarse problem, then you can have quite good scalability in 20,000 processors. In the first case, here the coarse problem now cannot be masked anymore by the fine one, and we start have some degradation. And in the second case, when we have a slightly larger global problem, we can get perfect scalability till almost 30,000 processors using direct solvers. But we know that direct solvers are quite expensive in terms of memory computation. So now we want to exploit the fourth property of the VDC methods, which is that we can approximate the local problems by, for instance, a 180 design. So we're going to use it and see what we get. So we have seen that the VDC method is an effective preconditioner, but since we are using for the moment sparse direct method, it's quite computational in memory management. So we use ANG, and we know from the numerical analysis that as soon as you have an optimal preconditioner, the method is also really scalable, as it was proved by Santiago. So we are going to do this. We're going to go to the next VDC method in light of the future parallel architecture, in which we will have much more limited memory per core, and because we want to go to high core counts, and we don't want so bad loss of scalability when the coarse problem starts to dominate. So which are the problems that we have to solve in the VDC method? We have one local derivative problem. We have one local constrained Neumann problem. For the computation of the basis functions, we have the same local constrained Neumann problems to be solved. And finally, we have a coarse problem that has to be solved. But the good thing is that we can approximate these methods. For the local constrained Neumann problem here, and for the coarse problem, the only thing that we need is one agency. For the local derivative problem and the computation of the basis functions, it's a little bit tricky, but you need something else. And rule space property has to be preserved, but it requires just a correction, and that it is very simple, it's very cheap, and it does not require to touch your ANG solver, so it's not important. So we implemented it, and we check which is the scalability of the method now with the nasal solvers. We run our code into Queen, usually, we include
We solved the same Poisson problem, the same setting as before. We increased the number of cores, and now the situation is somehow, it's hard to get scalability because we are using a serial AMG preconditioner, and we are using only one core for the course problem, when we have, in the last point, we have 93,000 cores for the final. So you can imagine that's how hard to get scalability here. And the local problem size is about 16 to the cube, so these are the figures that we got. So this is the number of iterations. We are using the following. I'm not going to explain why, but we're using two AMD cycles for the computation of the basis and for the random problem, and one AMD cycle, very simple, for difficult and post problem. So these are the number of iterations that we get with our method, with VDVC next activity method, with our implementation. This is the number of iterations. It remains constant, so everything is as expected. And when you go to time with our overlap implementation, you can see that in 30,000 processors, more or less, you still have the cost problem can be masked by the fine problem, so you have perfect scalability. At this point, the cost problem starts dominating, and you have some degradation in scalability. And now it's nothing compared to a Spartan method because the degradation is much small. We have 11% of degradation in almost 100,000. But please remember that we are only using one core for course duties in this example. And the other thing is that we are not using all the memory that we have per core, which is not much, it's only 1 gigabyte. So we could even go to larger problems, larger local problems, and get better results. If you want more info, you can go to Implicit talk on Friday morning. So now that we know how to work with the second physics problems, simple problems, how to go to quite large core counts, let's go to multiphysics. But before going to multiphysics, let me talk a little bit about the CFD solvers. So here, let's start with the stock system, transient or steady. This is the system matrix that we have. Here is this matrix here, plot for the velocities, includes the inertia terms and the viscous terms, gradient divergence, and this matrix here can be zero using superstable elements, or is the semi-positive definite matrix if you are using stabilized kynetic. So for solving this problem, we have like two options. One is to use block preconditioning, in which, okay, we have our matrix for the Stokes problem. We use a block reduced factorization. This is quite a standard word. And now we have the full complement. It has the following expression with f minus 1 here, so it's hard to work with it. And finally, we need to precondition somehow to approximate this. So the typical idea is to put this block here and probably precondition f and certainly precondition s. So at the end of the day, you have to solve a problem for velocities and a problem for pressures. So the key for this kind of methods is an efficient preconditioner for the full complement. So we have different options. For instance, Sawa for the sticky problems, Deutsch-Abarth preconditioners for transient problems. In any case, they involve the inversion of f, which is mass matrix plus a vector Laplacian, we can easily solve it. And for the pressure problem, we have for a mass matrix, obvious, or a Laplacian problem that we know how to solve quite well. So we can apply that, we can combine this and replace these matrices by the VDVC preconditioners. Instead of an f, we are going to put the VDVC preconditioner of f. Instead of the Schur complement approximation, when it's Laplacian, we're going to put the VDVC approximation of this Laplacian matrix, and if you have the mass matrix, we are using just the Schur matrix. So this is what we're going to do in the first approach. In the second approach, we straightforwardly use VDVC for the Stokes problem. This is what was proposed by Implicit and workers. The theory is not fully understood when you have continuous pressures, which is our case. Only for these continuous pressures, but okay, this is the VDVC problem. Now, the spaces which you look for the velocity and for the pressure are the original spaces, but with this relaxed continuity that I connected before. So, the only thing that we can prove is that at least the preconditioner is well blocked. You can check that if you have a method that's stable because it's in superstable or because it's stabilized, when you consider its VDVC approximation, the VDC problem is also stable. This is inspired by the non-conforming Kussner-Abelard theory. So we can apply it. It is well posed, even though we cannot get conditional numbers. So these are the results that we obtained for the Stokes problem in 3D using areas in Japan. The same setting as before, but now for the Stokes problem, B-driven type cavity problem. And we consider 3 different ways to solve this problem. The monolithic problem, the block problem with exact solvers, direct solvers, and the block preconditional approach with inexact solvers, with A and G, for 2 different problem sizes. So here are the results that we obtained. I'm only showing time. So you can observe that somehow the monolithic approach is quite expensive, and it seems that the block approach is very interesting. So when you go to larger, this is the 32K nodes per core. When you go to larger local problems, we cannot even solve the monolithic approach because of the memory requirements. But when you go to the block preconditioner, just so that it's usually better to go to the exact solvers in this case, also in terms of memory and the time. So, okay, I have to say that we don't have yet an inexact monolithic VDC method. We are working on this. And you can also have more details in Alberto Martin's talk after this slide. So, how we work on Navier-Stokes equation is the same idea. We don't want to get into details, but we can also use block preconditioning for Navier-Stokes equation. You probably know the pressure convention diffusion type preconditioner by K and coworkers, so we use it. In this kind of preconditioner, we have to solve the Laplacian problem for the pressure. We know how to solve it. Conventional diffusion reaction type problem for the pressure, and a mass balance. And you can also extend the VDC for conventional diffusion reaction. It's quite simple. We only change the interface conditions and some other things that you can also apply to this kind of problem. So with this, we are now solving LES simulators of incompressible flows. There is a talk by Irremediably tomorrow in the morning. And now, how we go to multiphysics. No? So the idea is that you start with any multiphysics problem. How can you solve this problem? So our approach is the following. We're going to use what we call recursive block precondition. The idea is that you have whatever multiphysics problem you have, you reblock your problem into a 2 times 2 block system. Here you can have as many as known as 1 in X, 1. So you reblock your problem into 2 times 2 block system. You define an inexact factorization of the method, as I presented for the Stokes problem before, and define. And here you have now some preconditioners for F and for S in this process, where S is the true complement for inexact factorization. And if these blocks include more than 2 variables, you start again and perform again block precondition. So this is what we have used for our, here again, the key is how you define the approximation for the true complement every time that you do this. So this is what we're applying for MSD applications, but I want to show you only inductionless MSD applications. So we work with this because this kind of problem, inductionless MSD, is quite interesting for the design of building blankets in fusion reactors. But we have to simulate our liquid metals with extremely large magnetic fields, and we can assume that we have incompressible fields. So this is the system of equation that we have to solve. It includes velocities, pressures, and here we have the current density and electric potential. So this is the problem that we have to solve, and this is multiphysics. We have 4 different types of unknowns. The coupling among the two problems comes from the Harman number. For large Harman number, the problem is tightly coupled is hard to solve. So as I said before, we also apply all this framework for resistivity, but I'm not going to talk about that. After the discretization of this problem, linearization, and iteration, what we have to solve is a problem this type, 4 different unknowns. These are this is the matrix that we have to solve, and here these C's are the coupling matrices between the 2 subproblems. So what we're going to do is first we will block the system into 2 parts. We have 4 unknowns, and this is one of the methods that we have. We have some other, but we're going to present only one. First, we split the problem like 2 different subproblems. One for the electric unknowns and one for the velocity and pressure of the fluid. So here, as a block preconditioner, we use This one is going to be exactly this approximation. And for the Schur complement that we take from here, we can check, if we're working a little bit on it, that we have this term plus an additional term. And the good thing is that this additional term is of the order 1. So since we wanted methods that will be optimal, we are going to omit this error here, and we expect that it will work well as we reduce the mesh size. And we see that this is the case. So now we have an approximation of the Schur complement in the first level of proportion. So now we go to the second level, you have J and phi, so again, we apply the same approach, and we decompose this problem into sub-problems, same approach as before. Now the Schur complement can be easily approximated. This is nothing but some kind of unique Laplacian problem, so it's very easy to approximate the Schur complement and Laplacian conflicts. And for the second problem, this is nothing but the Bierstok's equation, so we are using the pressure convention preconditional. There are lots of theorems in this case. So at the end of the day, what we get is 4 different quantum physics problems to be solved. And then we can apply our solvers, our quantum physics problems, quantum physics solvers. So if we check the number of iterations, what we observe is that, as we expected, when we start using mesh, the method works better. And something which is quite good. Here we have very coarse meshes for testing. That this is a good thing, the fact that the number of iterations that we require for this conditioner is reduced as we increase the as we have reduced age. On the other hand, with regard to the Harman number, this is very important because for the obligation that we have in mind, we have to deal with very high Harman numbers. So the method is doing a quite acceptable job with respect to the Harman number. That's not one. So we have applied this for just blanket simulations in which the Harman number was like 15,000. It was very large, and we got quite good results. That for more details, you can go to Ramon Blackstock on Friday morning. And we have also applied this framework now, for instance, for thermal LHD applications. In fact, the implementation that we have of all these things in MPAR is quite abstract, so it's very easy to introduce new preconditioners in our set. So just as a conclusion of this talk, first I introduced a highly scalable implementation of Implicit methods. The idea is to overlap coarse and fine duties. We have also used AMG for local problems in order to boost the scalability. Then we went to CFD problems, and we have compared monolithic and block approaches for this kind of problems. The precondition to say that show better performance. And finally, we went to multiphysics using this recursive block preconditioning, split things into quantum physics problems, and then apply an hypothesis over there. And now our work is to combine this inexact overlap implementation with a multi-level implementation in which the coarse solver now is also distributed, so you can mask in a much larger, for a much larger core count, the coarse problem with the final. So this is the work that we are doing now with different levels in the VDC method that this is before. We hope that we can go much faster.
Yes, please.
What would be the difference between this approach and the hybrid positive approach? Are they kind of similar, or is this completely different?
In this case, it's quite different to the hybrid state. I mean, you have like one wise continuity, for instance, on the corners. It's like it's different, but somehow they say the VDC method applied for DG would be more similar to the approach to the NDG method because we're also like doubting nodes and we're working with jumps, we're introducing iterations on basis. We are not really doing this
last question. So have you got any backward analysis for the VDDC kind of approach where you basically perturbing your matrix, stiffness matrix by splitting your domains, introducing the perturbations actually. So you're solving, instead of solving Ax equals B, you're, I think, solving A plus delta A times X plus delta X equals B. So how far is your delta A from the actual system that you're solving, that you urgently want to solve?
You say when I use natural solvers? I'm not sure I understand your question.
So it's essentially, I'm talking about backward analysis of the system that you're actually solving, because by splitting your domains, you're perturbing your system. You're introducing a perturbation.
Well, this has to be, all these methods have a very deep mathematical analysis that is quite well understood for some problems. Let's say that they are well understood and you know which are the condition numbers that you're going to get. So in this sense, the theory is quite close for some problems. Some other more complicated problems, it's not so obvious. And for these simple problems, the theory is quite mature.
But it's less about the source of the problem and more about the method that you use to solve your linear system. Well, maybe we can discuss offline.
Okay, so thank you again.